number 1 with chapter 7. That's the last of the trigonometry topics. So from here on until you see the final exam or whatever, you can say so long to sine, cosine, tangent.
Is that a good thing or a bad thing?
I don't know, just a thing. Just telling you. Okay. So the remainder of this semester is going to be largely topics from that you've seen in Algebra and Algebra 2. Just we're going to maybe extend a little bit or go a little bit deeper here or there. But in general, this stuff should be pretty familiar. So that's good, right? So if it's less... yeah, well, like years of familiarity versus like just a semester familiarity. So in the supplement A, we're going to be talking about solving systems of equations. So when we talk about a system of equation, there's two things that we have to specify. You have to specify the quantity of equations that we're trying to solve over and the type of equations you're using. So we're going to start by talking about systems of two linear equations. So 1, 2 linear equations of the form ax plus by equals c, dx plus ey equals f. A, b, c, d, e, f are all just real number constants. So to do this, to solve a system, what we need to do is find an xy that satisfies equation 1 and also satisfies equation 2. Now, if we want to construct a method to do this, one way is we can think about this problem graphically, right? Equation 1 represents a line, and every xy that satisfies this equation is just a point on that line, right? Equation 2 represents a separate line. Every xy that satisfies equation 2 is just a point on that line. So the solution to that system is going to be an xy that appears on line 1 and an xy that appears on line 2. So we're looking for the intersection of the two lines. Yeah. So let's grab an example here and kind of run through how we could do that. Now that we've kind of talked through the motivation. So if I want to solve this system by graphing, I'll start with my equation 1. And I'm going to start by trying to rewrite that so that it's in slope-intercept form. Y equals mx plus b. What do I need to do to this equation to get it into slope-intercept form? What's up? Get y by itself. Great. How am I going to do that, though? Subtract 4x from both sides, right? Everybody feel good there? Now, to graph this line, how many points do I need to graph a line? 2 would be sufficient. 3 is fine, but you don't need the third one. So to find points on the line, we're just going to pick some values for x and find the corresponding value for y. So let's say I pick 0 for x. What does y have to be? 8. So we plug 0 in for x. Negative 4 times 0 is 0. And then plus 8 is 8. And then let's say I pick 2. What is y? 0. 2 times negative 4 is negative 8. Plus 8 is 0. Did it matter which x's I picked? No, I'm just going to pick things that look convenient, right? All right, so now I'll move on to equation 2. Well, we're not done yet. So again, I'm going to do the same things. I want to get equation 2 into slope-intercept form. How do I do that? Subtract 2x from both sides. Great. And then what? divide by negative 3. So negative 2 divided by negative 3 is positive 2/3. And 18 divided by negative 3 is negative 6. We'll do the same thing. What x's should I pick? 0 sounds like a good one. What's the y when I pick 0? Negative 6. What's another one? I wouldn't do that. I mean, you could. But what's the problem with picking 1? We get a fraction, right? Barfaruni. What values of x could I pick so that I don't end up with a fraction for my y? Multiples of 3, right? So, for example, positive 3 would be fine. What do I get when I multiply 2/3 by 3? 2. Very good, Kate. Right? You make a common denominator, or you multiply straight across 2 fractions. 2 over 3 times 3 over 1 gives you 6 over 3, reduces to 2, and then we have to subtract the 6 still. So that's negative 4. Everybody feels so far so good? This is like algebra 1 algebra, but we got to do it. All right, let's plot some points. 1, 2, 3, 4, 5, 6, 7, 8. I got to go down to negative 6 still. 1, 2, 3, 4, 5, 6. And then 1, 2, 3. All right. So plot my first point. There's 0, 8. There's 2, 0. I'll get my ruler out here. It's probably pretty good. Okay. And now I'll plot the other pair. So I have 0, negative 6, and then 3, negative 4. And then I'll grab my ruler again. Oops. Okay, that looks pretty good. And what do I see? There it is. What does that appear to be? 3, negative 4. Everybody okay with this? Now, I can check this to be sure. To check this, all I'm going to do is plug in that solution into my x and y. And I'm going to plug it into both equations and make sure that they both work. Oops. So 4 times 3 is, and then plus a negative 4 is. That one works, right? 2 times 3 is, and then minus 3 times negative 4 is 12. Yeah. Okay, so that checks out. So we know we're done, right? Everybody feel okay? All right, what's the drawback here to what we just did? Takes up some space. It takes a little bit of time, right? What else is an issue, though? Potential issue with this? What's up? Oh, well, that's not, you're kind of on the right track. What if the solution was something like, instead of 3, negative 4, what if it was like 2.9, negative 3.9? Is that going to be easy to tell by the graph?
Yeah.
Not really, right? Now, if you wanted to make like tick marks to the 10th place, you could draw an accurate enough graph for that to happen, but like, yuck. right? That doesn't seem real appealing. What if the solution was like 14,256 comma negative 12,982? That's going to be a big graph, a lot of tick marks, right? So like there's nothing wrong with this method in theory, but in a practical sense, it's like tedious, right? It can become really tedious and time consuming when it doesn't need to be. So one workaround we can have is that we can use a machine to do this, right? Because our calculator, the size of the numbers doesn't really matter to the calculator. The calculator is infinitely neat. It can carry as many decimal places as it needs up to its memory capacity. I don't know, it's like, I think it carries like 100 decimal places or something. So that's an option, right? So let's show you how to do this same problem on our graphing calculator. If you have a graphing calculator with you, I invite you to take it out so you can follow along. If not, you can just go back and watch this with your graphing calculator at home if you don't have it with you. Or if you think you're like, I just have an excellent memory, I'm just going to watch it and I'll be good. Maybe you're that. Okay. So what I did, I turned on my calculator and began by pressing the y equals button. That's the one in the upper left-hand corner on the big home row at the top. From there, I'm going to type in my y-intercept equation for equation 1. So that's y equals negative 4x plus 8. Notice the y equals is already built into my calculator. So I'm just going to type in negative 4x plus 8. And then in the second line, I'm going to type in my second equation. So again, the y equals is already there. So 2/3 x minus 6. Everybody's good with that? It's been a minute since I've graphed anything. I have no idea what my viewing window is like. So I'm going to press zoom and then pick option 6 for zoom standard. That's going to reset my window back to the standard negative 10 to 10 in case I was graphing something kooky and I changed my window for whatever reason. So I'm looking at my picture here. That picture looks exactly the same as the one that I just drew. It was a little bit less effort for the calculator to generate that than it was for me to generate it, but looks like the same picture. Now, here's our solution. The calculator can actually tell me what that is without me having to read it. So if it's just really close to 4, negative 3, the calculator would be able to tell me. So to do that, have the calculator find that intersection for me. I'm going to press the second button. That's the blue one. And then the trace button, which is up there on the home row. All of the commands in this menu are things that you can do to a graph. Of these commands, which one sounds like the one that we're going to want? Intersect, right? So let's go pick command 5. Now, at the bottom, your calculator is going to ask you a series of questions. It says, okay, you're looking to find the intersection of something. Well, you have to tell me what things you want to find the intersection for. So it says first curve. So notice my cursor up here is flashing. It's on this line here. Well, that's one of the two things I want to find the intersection of. So I'm going to press enter. Notice my cursor is now toggled down automatically to this line. Well, that's the other line I want to find the intersection of. So now it says second curve. Well, I'm on my second line, so I'll press enter there. And then it has a guess. How many times do you see these two lines intersecting? Once. So the guess here doesn't matter because there's only one intersection. The calculator is going to find it as long as it's on the screen. So I just press enter wherever the cursor is. If you had multiple places where it intersected, then you'd want to make sure your guess was close to the one you were looking for. But here it doesn't really matter. And there it spits out the intersection is 3, negative 4. Everybody's okay here? All right. So we've seen that our system of two linear equations can have one solution to it. Could I have any other things happen other than just one solution? What else could happen? What's up? Great. What's that mean? What's that look like in the picture? Well, are there any intersections? Yeah, what's it say, Jacob? Yeah, they're coinciding, or they're just the same line. One line right on top of the other. That means that every point on the line is a point on the other line, because they're the same line. So you have infinitely many points on the line, you have infinitely many intersections, you have infinitely many solutions. The other thing that can happen is if they're parallel. How many things do you have in common there? 0. All right, so oops, where did that go to? So we have these 3 possible situations. Wouldn't it be nice if I could look at my equations at the start before I even try to graph anything and be able to tell which one is which?
Yes.
Yeah, right? So let's go back and look at this first one where we got one intersection or one solution. If I look at the slopes, notice they're different. As long as the slopes are different, we're always going to get one solution. Everybody's okay? If I have 2 lines that are just overlapping like this, it meant they're the same line, right? So the slopes have to be the same, and the y-intercepts have to be the same. Everybody good with that? If they're parallel, well, I remember from geometry, parallel lines have the same slope, but they're not overlapping. So the y-intercepts have to be different, right? Like this y-intercept is 1, and that one looks like it's 6. So just by looking at my equations, I should be able to tell whether I have one solution, infinitely many solutions, or no solution. Does that feel okay? Let's look at an example where we do that. All right, so just like before, my first order of business is going to be to rewrite these into slope-intercept form. So what do I have to do here for the first equation? Minus 4x, and then divide by -3. Everybody okay there? Okay. And then we'll do the same thing for the second one. So we'll subtract the 8x and then divide by -6. So negative divided by negative is positive, and positive divided by negative is negative. So I have that. What do you notice that we can still do with that equation, though? Reduce those fractions. Great. What does 8/6 reduce to? 4/3. And what does 16/6 reduce to? 8/3. And what do we notice here? They're the same. So what's going on? Infinitely many solutions, right? Done. I don't have to graph anything because it's just infinitely many solutions, man. So that's all there is to it. Feel okay with that? Okay. All right, what if now instead of having equations, we have a system of inequalities. Remember, when we say inequalities, we're talking about like less than or equal to, greater than or equal to, greater than, less than, stuff like that, right? So if I have a system of linear inequalities, I can have 2, 3, 4, 5, 6, 100 inequalities in my system. I don't have to have just 2. Now, you're never going to have to do something with 100 inequalities in it, but like, you could. If we have a system of inequalities, we're either going to have infinitely many solutions or no solution. Now, that's a pretty boring outcome, but we're going to want more than just stating infinitely many, right? We're going to want an illustration of where on our xy axis those infinitely many solutions occur. So our answer is going to be a picture where we've described where those infinitely many solutions live. So look at our example here. We have 3 curves, or 3 inequalities. If I take the first inequality, I'm going to start by rewriting this so it's in slope-intercept form. So we'll subtract the 3x over, and then divide by the -5. What do I have to remember when I divide by a -5 here? The inequality symbol reverses directions. When we divide by a negative, same thing if we multiply by a negative. I'm then going to pretend that that is a equation, and I'm going to find the points on that line. Everybody's okay so far? So let's see, I'm going to pick 1. So 3/5 plus 2/5 is 5/5, or just 1. And then what do I need here? 6 would be a good one. 3/5 times 6 is 18/5, plus 2/5 is 20/5. That'll be 4. Again, could you use decimals if you wanted to? Sure. But, like, I'm going to pass if I don't have to, right? I'll pass on fractions if I don't need to use them. All right, same idea here. We're going to add 12x to both sides and then divide by, oh my goodness, guy, that's a y now. Then divide both sides by 7. Since I'm dividing by a positive number, nothing is going to switch places. I'll pretend this is an equation then. And now I have some yuckarooskies here. Let's see here. Let's see. 2015, no. 27, no. 39, no. 51, no. Well, that won't work. 63, okay, 5. 5 times 12/6 is 60, plus 3 is 63. 63/7 is 9. And then if I go the opposite way, let's see. There we go. If I do -2, -2 times 12 is -24/7, plus 3/7 is 21/7, which is -3. Fantastic. Are you impressed with how quickly Mr. Kula can find those guys? You don't have to be. It's not that impressive. All right. Last one, we're going to get the y by itself. Is it weird that there's no x in this one?
No.
It's not a big deal. I'll just divide both sides by 2. The y is by itself. I'll make my xy table. Let's pick, say, x to be 0. What do I do? Where do I plug that in? Oh, I should write as. Sneak that in there. Where do I plug the x in? Is there an x in the equation? No, but what does it tell me y is? Y is 9/2, right? So whatever x is, y is going to be 9/2. Yep, it's going to be a straight line. What kind of line? Horizontal or vertical? Very good. If it was x and no y, that'll be a vertical. Everybody feel all right? So far, so good? All right. So now, what I want to do is decide whether the lines that I'm drawing are going to be solid or dashed, and whether I should be shading above the inequality or below the inequality. So all of that information is told to me by the type of inequality I have. Well, actually, not. I want to look at this inequality. So because it's a greater than or equal to, the or equal to tells me the line should be solid. And because it's greater than, it tells me that I should be shading above. For the next one, since it's strictly greater than, that tells me it should be dashed. And again, shading above. And for the last one, since it's or equal to, it tells me the line is solid. And since it's greater than, I'm going to be shading above. Everybody feels okay with that? Now let's draw our picture. Okay, let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6. 1, 2. All right. So I have 1, 1, and then 6, 4. So get my ruler out here. And I'm going to draw a dashed line. And I'll draw like an arrow pointing above to remind me I'm going to be shading above this one. The blue, we have 5, 9. And then -2, -3. Oops, I forgot to put any negatives down here. 1, 2, 3. Grab my ruler out again. Seems okay. This one is a solid line. And again, we're shading above. So do that. And then my last line is y is 0, 9/2. 9/2 is like 4.5, right? 1, 2, 3, 4. And solid line. or shading above. Everybody okay with what I've drawn so far? All right. So let's kind of do our shading in. So if I'm above the red, I'm there. If I'm above the blue, I'm there. And if I'm above the yellow, I'm there. So if I look, where do I see all three colors overlapping at? Like in this region in here, right? Does everybody feel okay with how I did that? So that's what your answer would be, is that region shaded. Cool? Okay. Do we feel okay doing this? Again, you probably remember doing this in Algebra 1 and 2. You certainly did it. Whether you remember it or not, well, you know, that varies by person to person, right? You guys feel all right on doing this, though? Is okay? All right. So, as we mentioned before, solving a system of equations by graphing is kind of stinky, right? It takes a lot of space. Potentially, like, it can be really tedious because neatness counts and like precision counts. And like, yeah, okay, I could do it on my calculator. Oh, speaking of calculator, let's do this first. We can do this problem on our calculator too. Let's show you how to do that real quick. I'm going to take a pause and digress to do this because I should have done it right away. All right, I'm going to take my 3y equals equations and then type them into y1, y2, and y3. Sorry about that. I got carried away and I forgot to do the calculator part. You guys would have been sad if I didn't show you how to do this. Okay. So to make the calculator now shade, to turn these into inequalities, what I'm going to do is I'm going to move my cursor so it's in front of the equation. And if I press enter, it'll cycle through some of the options. Right now, it's going to write this thin, straight, or thin solid line. If I press enter again, I have a thick solid line. If I pick again, I'll have shading above the line. That's what I want, but I'm going to cycle through and show you the rest of them. This is shade below the line. That's going to be like, it shows like a circle as it traces the line in. It looks like a pencil's drawing it. This one, it just shows the little tracer, but it doesn't create a line behind it. This one is a dashed line. So I'm going to do shade above for all of these because they're all greater than or equal to's, right? So I'm going to change these all to shade above. And then if I hit graph, there's my red equation or inequality. There's my blue inequality. And there is my yellow inequality. And we can see this region up here is the place where all three of them are overlapping. Is that pretty neat? Bet you know your calculator could do that. Maybe you did. But I think that's pretty handy. Okay. Sorry. Back to solving equations. We mentioned graphing. Effective, yes.
So the new calculators is just like an option. It's just different.
Yeah, probably. Like
it's just like a menu that I can go over under -0, 0, a few other options.
Yeah, probably. I don't know. I don't have the newest the newest calculator. I think even these ones aren't. I think they changed the operating system or something. Yeah. So even on the old ones, they had, or this one still had the old same or close to the same operating system. Anyways, so algebraically, we'd like a method to do this that doesn't require a graph, right? Because if it's algebraic, the number is the number. I'll just get the number, and then like I can be as precise as I want, right? So do you remember the two methods that we use to solve systems of equations?
Elimination,
Substitution and elimination, that is correct. So let's do a quick run through an example on these. So for a substitution problem, we need to pick a variable to solve the equation for. Basically, we're going to pick either x or y and try to get that variable by itself in one of the two equations. We're going to take the answer to that and plug it into the unused equation. That'll reduce that equation down to one type of variable, either x or y, allowing us to do like algebra 1 algebra to solve for the variable. And then we take that answer and plug it back into a two-variable equation to solve for the other, right? So it doesn't matter which equation we use and which variable we get by itself, but we can make our life easier by choosing well here. So look at equation 1 and 2. Which variable from which equation would be the one that Mr. Kulik would suggest getting by itself? The x from equation 2. Why is that? Because we don't have to do any dividing, so we know we won't create any fractions. My goal when making this decision is to try to avoid having to do fractions. Not that it makes the problem any more difficult, it just slows everything down a little bit, right? It's just a hassle. And my life goal is I don't want it to be hassled. Let me do it the easiest way. If I have to stop and think about it for a minute to make sure I'm choosing the easiest way, I'm okay with that if it means I can avoid something that I don't want to have to deal with. All right, so I'm going to pick equation 2, and I'll get the x by itself. I'm then going to take that value for x and plug that into equation 1. So everything else from equation 1 stays the same, except for where x is, we're going to write negative 3y plus 3. So far, so good? Now we're just going to do some algebra 1 algebra to solve for y. So distribute our 2 through. I'll combine some like terms. Subtract 6 from both sides. And divide by negative 1. There's half of our answer, right? So to get the other half of our answer, to get the x, I'm going to take this solution for y and plug it in to any two-variable equation. Excuse me. Which one do you suppose Mr. Kulik's going to pick? I'm going to pick this one. Why? Because the x is already by itself, right? I don't have to do anything to both sides. I just have to like plug in the number and evaluate. Now, I could certainly use one of the other ones. It's not wrong to do that. But like, I just didn't have to do any algebra here. Again, Mr. Kulik's going to say, what makes my life the simplest? That's the way I want to do things.
I feel that.
Right? It's not wrong to do it another way, but like, work smarter, not harder, you know? Everybody's cool? Does that feel all right? You remember doing this? At one point, you probably were pretty good at this, so it hopefully comes back pretty quick. The other method we want to talk about is elimination. So in elimination, what we want to do is pick a variable, either x or y, change the coefficients in our two equations so that our chosen variable's coefficients are opposites. So maybe one is 5 and the other is -5. We add the two equations together then, which causes that variable to eliminate. The resulting one variable equation we solve, and we plug that answer back into any two variable equation to solve for the other. So again, the choice in the beginning is I need to choose which variable do I want to eliminate. So look at the two equations, look at the x's and y's, look at the coefficients. Which variable do you suppose Mr. Kulik would suggest choosing to eliminate? X. Because to make 3 and 6 have opposite coefficients, I just need to multiply the first equation by -2. And I don't have to do anything to the second equation. If I tried to do this for the y's, I'd have to multiply the first equation by like -8 and the second equation by +7. Those are harder multiplication problems, and I have to do it to both of them. I would just assume I have to do it once if I have to do it. Or not at all. Sometimes you can get away with not having to do it at all, which is super cool. All right, so -2 times equation 1. That's going to give me -6 plus x plus 14y equals -20. And then we're going to add to that just equation, regular old equation 2. And then we're just going to add down. So those cancel out, and I'm left with 6y equals -12. Everybody's cool? Divide by 6. There's half of my answer. I'm going to take that half answer and plug it back into any two variable equation. I don't know, I'm going to pick this one to plug it back into, just because the coefficients seem a little smaller. So 3x minus 7. And then instead of y, I'm going to write -2 equals 10. Oops, that's -10. So -7 times -2 is 14. Oh, no, that's +10, you dumbo. Sorry. Okay. So 10 minus 14 is -4. And then I divide both sides by 3. I get -4/3. So my answer is -4/3, comma, -2. Boy, that looks like that would have been a pain in the butt to get by graphing, right? Yeah. All right, we have one little piece dangling here that we need to address with this substitution elimination idea. And that is, what does no solution or infinitely many solutions look like? Right? So let's look at that idea. So say we're doing a substitution problem, and we got x equals to whatever, some stuff. So I plug in, I have like 2 times that stuff minus 6y equals 10 or something. Everybody's okay? You kind of see what I did, what I'm trying to say? Is I got one variable by itself and I plugged it back into the other equation. If when I simplify, I get like 5 equals 10, like all the y's canceled out when I simplified and I'm left with just constants. Does 5 equal 10? No, right? What does that tell me? No solution. But what if I had gotten like 10 is equal to 10? Does 10 equal 10? Yeah, that means infinitely many solutions. So if you get like a true statement where the variables drop off, and you have something equals the same, just means infinitely many. If you have something equals not the same, that's no solution. Does that make sense what I'm trying to say here, folks? Okay. Now for elimination, if I take equation 1 and I add equation 2, well, maybe I do like, like 3 times and then like -2 times or whatever. And I get 0 equals 0, where the entire left-hand side canceled out and the entire right-hand side canceled out. What's that telling me? Infinitely many solutions. But if I got like something like that, tells me no solution. Actually, it'd probably be the reverse, right? Well, here it should be like everything on the left will just cancel out, right? Because the only thing on the left are x's and y's. But that's what that's saying, right? So that can happen. It's okay if all the variables go away and you end up with no solution or infinitely many solution. The one thing I would caution you about, though, is if you're doing substitution and you get a whole bunch of infinitely many solutions, or you get an infinitely many solution and you check in the back of the book and that's not the answer it's supposed to be, the most common mistake is that when you solved this for x, you plugged it back into the same equation, right? So you got equation 2, you got the x by itself, and then you plugged your answer back into equation 2. Every time you do something like that, you're going to get infinitely many solutions. It has to go into the other equation. So if you're getting like infinitely many solutions all the time when you're doing substitution, you're just plugging back into your same equation, which is not what you want to do. All right, I'm done. You guys feel okay? This should have felt pretty comfortable, I hope. At this point, you guys should be able to do 1 through 18. You got about 30 minutes remaining here in class. I would say you can get a whole big chunk of that stuff done inside of 30 minutes. So takes out your stuff and get crack-a-lackin', If you need to borrow a calc, I got a couple on my desk. I'm happy to share. Everybody happy? Or relatively so? Your math class happy anyways?
Yes.
I guess.